So for the fourth problem, we're computing an integral, x squared dv, whatever that is, over a region E, and the regions between x squared plus y squared equals 1 and x squared plus y squared plus z squared equals 4. I encourage you to pause at this moment and try to draw a picture for what these two regions look like and how E is shaped. Okay, so the second one is a sphere with center at the origin and radius 2. And the first one is a cylinder. So I particularly like when you have these spheres converting things to the xy polar picture and then the rz picture, like in the last problem. So let's explain how to do that. So maybe at some big picture level, this cylinder has radius 1 and the other sphere has radius 2. So I know that my overall image for this problem should be in my head is that I have this radius 2 sphere, and then inside of it I have, if I stop here at radius 1, I have a cylinder. So that's going to look like, and it's going to run into this sphere and then continue on out below and above. And so what I'm interested in is that region outside of the cylinder and inside of the sphere. One way you should think about visualizing this, if this is hard to visualize, is this is an apple that has been cored. So you've taken a sphere and you've punctured a cylinder straight through the middle to remove the core of the apple, and I want to know how much, I want to integrate this function over the remaining region. I am going to say, though, I don't think this picture matters that much. I think it's good for checking yourself, but you can also get to this answer without drawing this, only by drawing the xy and the rz planes. So let's do that as well. So in the xy plane, the function I'm looking at is a cylinder, right? And I need to look at this this other, so that's clearly the cylinder, r equals 1, and this is coming from the first equation, x squared plus y squared equals 1. However, we also need that second equation to matter something in determining our region. And so if you look at x squared plus y squared plus z squared equals 4, well, this is the plane z equals 0. So we should plug 0 in for z, and what we get is another circle of radius 2. Okay, so that gives me this little annulus, this punctured disk, which is the region in polar coordinates that I'm integrating over. That's the base of my region. Over here in this sphere, that's the region that's here. And hopefully that helps see what we're doing. Okay, so for these bounds, I'm going to use r goes between 1 and 2, and theta goes between 0 and 2 pi. And r, depending on theta, r doesn't change, so they're constant. They're somewhat interchangeable here. This is a nice region in polar coordinates. Okay, I'm going to scroll down a little bit. The other function we need is z. I claim the z r plane. And if you take this other equation we have, x squared plus y squared plus z squared equals 4, that's the same as r squared plus z squared equals 4. And this is, in this plane, a circle. Yeah, no, always take two stabs at every circle. So, okay. No, even worse. Okay, there we go. Radius 2 circle. Cool. So, now again, you should imagine if you spin this, you'll get the sphere that's the outside of this region that we care about, right? So what we're going to imagine is that we are doing our integration. So we've kind of like picked some angle theta in the polar plane, and then our next level of the for loop is we're going out in the r direction. And when we're at one of those points, and so I'm going to draw a big dot in the middle for that point, over here, that's a point in the xy plane. So that's over there at some r. It's an r in between r equals 1 and r equals 2, because that's what this other picture is telling me. And then I need to now integrate over the rest of the region. And so I'm out here. I'll draw this in the upper picture. I'm out at one of these points. I need to go up and down. And so I think about it as the lowest point in this region is down here. And up here, this is the highest z-coordinate. And so we're going vertically. So that looks much easier in the z equals r picture. That's starting here and going up to there. Okay. And that's it. And so you might notice that, in fact, because we're going over r equals 1 to 2, the region that we care about is actually just, and let's maybe do this in blue. Yeah. The region we care about in the annulus looks like this in this picture. And then when we integrate it, it's going to be this kind of little section of a circle. And so if you imagine taking that section of a circle and again spinning it around the z-axis, you're going to get this chord apple. You're going to get an apple that's missing this center section that's closer to the z-axis. Okay. So now I'm going to actually write up the integral bounds. So if you haven't paused and tried to do it based on my work so far, you could try doing that. So I'm going to do it just by looking at these two pictures, the polar picture, and the ZR picture. Okay, and in these two coordinate systems, oh god, I need to go check what my original function was. X squared dv. Okay, x squared. Let's write this. We have x squared dv over e. Okay. X squared becomes r cosine theta squared, all squared. So that's r squared cosine squared theta. dv becomes r dz dr d theta. And I really emphasize write this r separately, at least at first, so that you get used to writing it down. And now I'm going to fill in my bounds. So theta goes from 0 to 2 pi. R goes from 0, just kidding, R goes from 1 to 2, up in that polar bounds. That's from here out to here. And then in my z coordinates, z is starting down at this lower part of the circle. I know to go integrate over a circle, I'm going to have to do semicircles. So that's z equals minus the square root of 4 minus r squared. And it goes up to z equals plus the square root of 4 minus r squared. And there's your answer. These lecture videos are already going pretty long, so I'm not going to solve the rest of this integral. We could just leave it as a set up the integral problem. But I will promise you that if you do solve the rest of the integral, you'll actually discover that you don't have to do any trig sub. It's going to be a u sub problem. So when you're doing the dr integral, the one after you do dz, the square root with the r squared inside of it, you'll be able to set 4 minus r squared equal to u, and unfold the whole problem.